Hello students, in this lecture we will start the new chapter System of Particles and Rotation Motion. Relation between kinetic energy of rotation and moment of inertia. You know the magnitude of linear velocity of ith particle rotating about a fixed axis in terms of angular velocity is given by v is equals to r omega, and kinetic energy is half mv square. Put the value of v in this equation, and for the total kinetic energy you have to take summation of this ith particle varying from 1 to n. So the k will be equals to half of summation of mi ri square into omega square, and the summation of mi ri square is moment of inertia. So the kinetic energy of a body is equals to half of I into omega square. Now let's derive a relation between torque and angular acceleration. Analogous to the translation motion, when torque acts on a rigid body rotating about a point with constant angular velocity, then angular velocity of the body doesn't remain constant but changes with angular acceleration alpha, which is proportional to the externally applied torque. For this, consider a force Fi acting on an ith particle of mass Mi pivoted about an axis through point O as shown. This force Fi has two components, one parallel to the radius vector and another perpendicular. The parallel to the radius vector component doesn't have any effect on the rotation of the body, and the perpendicular component will affect the rotation of the body and produces torque, and the torque is equals to F into R perpendicular, or F perpendicular is the resultant force acting on the ith particle. Then by applying Newton's second law, this will be equals to mass into acceleration. Put the value of acceleration in terms of angular acceleration, that is R alpha. So torque will be equals to mi ri square into alpha, and hence torque is equals to I alpha. The moment of inertia into angular acceleration. Similarly, angular momentum will be equals to I into omega. Prove it by following the same steps, and also do a question that you have to prove that the angular momentum of a particle is equal to twice the product of its mass and areal velocity. Here areal velocity is the change in area divided by the time duration. Work done and power in rotation motion. We know that when we apply force on an object in the direction of displacement of the object, work is said to be done. Similarly, force applied to the rotation body does work on it, and this work done can be expressed in the term of moment of force torque and angular displacement theta. Consider the figure shown where force F acts on the wheel of radius r pivoted at point O so that it can rotate through point O. This force F rotates the wheel through an angle d theta, and d theta is very small so that we can regard force to be constant during corresponding time interval dt. You know dw is F dot ds, but ds is r d theta. So dw will be equals to fr d theta. Now F into R is torque. So dw is equals to torque into d theta. And the value of d theta, you can replace it by theta 2 minus theta 1, final minus initial, or delta theta. And the power is rate of doing work dw by dt. So it will be equals to torque into delta theta by dt, or you know that delta theta by dt is the omega. So power is equals to torque into omega. And in vector notation, it is the dot product of the torque and angular velocity. This force Fi has two components, one parallel to the radius vector and another perpendicular. The parallel to the radius vector component doesn't have any effect on the rotation of the body, and the perpendicular component will affect the rotation of the body and produces torque, and the torque is equals to F into R perpendicular, or F perpendicular is the resultant force acting on the ith particle. Then by applying Newton's second law, this will be equals to. Similarly, for any system, you have to take the total angular momentum, means the summation of Li, where I varies from 1 to n, and ultimately L is constant, means L1 plus L2 plus L3 up to Ln is constant. Similarly, angular momentum will be equals to I into omega. Prove it by following the same steps, and also do a question that you have to prove that the angular momentum of a particle is spinning of ice skater as shown in the two diagrams. Holding a pair of dumbbells, his axis of rotation is vertical. With the weights far away from that axis, his moment of inertia is large, as shown in the left side figure. But when he pulls his arms in as he is spinning, the weights are closer to the axis, as shown in the right side figure. So his moment of inertia gets smaller, and you know that L is equals to I omega is constant. So when he pulls his arms in, I will decrease and omega will increase, and he starts spinning much faster. Another illustration of law of conservation of angular momentum. A diver jumping from a springboard exhibits somersaults in air before touching the surface, because after leaving, a diver curls his body by pulling his arms and legs towards the center of his body, and this will decrease his moment of inertia, and he spins fast in mid-air. Just before hitting the surface, he stretches out his arms. This decreases his moments of inertia, and the diver enters at the surface with a gentle speed.